Good evening, everybody. It's like being at school. Good evening, everybody. No, don't have to do that. Welcome to Imperial College. It's great to see you. How many people have we got here who've been here before? Put your hands up if you've been. Oh, wow. Loads of you. Okay, so you're all pros at this, aren't you? Yeah? Okay. Well, I hope you have a great time tonight. Have you been able to enjoy some of the fringe activities out at the front? Yeah. Wow, look at that enthusiasm. There's like screaming yes, there's no's. Listen, if you didn't get to see it, it's carrying on till 8 o'clock tonight. So if you've got a chance before you go, you can pop in there on your way out, okay? So make sure you do. There's some really fantastic hands-on science stuff to take part in. Okay, this little chap may well be familiar to some of you if you've been here before. He is the mascot of the Children's Christmas Lecture, and he's turning into a bit of a diva, if I'm honest. He's demanding rooms and mineral water and all sorts. It's just too much to handle. So he's only 8 years old. Now, last year, we had somebody who was younger than 8. Have we got anybody younger than 8 in the audience? Anybody younger than 8? A few people. There's some rogue hands going up, and I really don't think you're 8. Yes, no, not. Anyone 9? Have we got any 9? Oh, look at the front. Oh, we've got 9-year-olds. Welcome, everybody. So the thing about Imperial is we're all about science, and we love everybody to enjoy the science that we do. And the younger you are, the better for us, because then you'll grow up really loving science. Okay, without further ado, I will be handing you over to Seb shortly. One bit of housekeeping. We are not expecting a fire alarm, okay? If the fire alarm does go off, follow the exits over there, and our lovely president's ambassadors, can they just wave their hands over there in the yellow T-shirts? They will be able to guide you out, okay? So we're not expecting any fire alarms. It's all going to be good. Simon and Jo have promised me there'll be no flames on stage. Lots of water, but no flames, so actually it should be absolutely fine. All right. Okay. Seb, this is your moment. No pressure. He's been practicing, bless him. He's done very, very well. Okay. Can we have a little round of applause for Seb first?
Welcome to the 2017 Children's Christmas Lecture. This year we are going to learn all about climate changes. It's a very important topic and we need to understand it really well. So I would like to introduce Professor Jo Haigh and Dr. Simon Foster on the stage. Put your hands together and give them a big welcome.
Thank you very much. Brilliant.
Well, thanks, Seb, for that fantastic introduction. And thank you all for coming. It's wonderful to see so many people here. So it's my job today with Simon. He's actually hiding behind the screen over there at the moment. He'll appear in a minute.
Hello.
To talk to you about climate change. So the first thing is to think a bit about what it is we're talking about when we talk about climate change. I'm a scientist, and so I'm afraid I love graphs. I've got a few graphs in this talk. It's not all graphs, but there are some graphs. So I hope you, like me, are fond of graphs because they're full of information. So this graph is showing the temperature for the last 150 years. And you can see it's sort of wobbling around, but actually it's going up towards the end. And this is what's become known as global warming, and it's definitely some sort of change that's going on. And this is what we want to understand, why it's happening, if it's a good thing or a bad thing, and if it's a bad thing, what to do about it. That's just showing you, if we start off in 1850, then we're about 1 degree warmer now than 150 years ago. Doesn't sound very much, does it, 1 degree? You think, 1 degree, what? You know, summer and winter is different than that. North and south is different than that. So why are we worried about 1 degree? Well, I hope I'll be able to explain some of the effects of that as I go through. So I'm going to talk a little bit about different factors that influence. So what things change the climate? What makes it get warmer and colder? and then talk about some of the ways that we measure climate. We measure temperature and pressure and humidity and rainfall and all the other things that give us measures of what the climate's doing. And then I'm going to introduce computer models. So these are the models that we use, or the Met Office and people use every day to forecast the weather, but we can also use them to forecast the climate. And I'll tell you a little bit about them, what might happen in the future, a little bit about energy use, and then what is going on the international scene to do something about climate change. So here we are, back to basics. We're on the Earth. There's the sun, not to scale. And all the energy that's driving the climate system is coming from the sun, none coming from anywhere else. There's a tiny, tiny bit of energy coming out the centre of the Earth, but that's negligible. So all the energy is coming from the sun. And so we're sitting here, bathed by the sun's lovely radiation, and the Earth gets hot, and it gives out heat radiation. So when it's in equilibrium, that means there's a balance. There's the same amount of energy coming in as going out. Now we know, because we've measured it, how much energy is coming in from the sun and how much energy is absorbed. And so we can calculate, if the same amount of heat is going out, what the temperature of the Earth must be. Easy peasy. We get minus 18 degrees Celsius. Hang on a minute, that's not right, is it? Is it minus 18 in here? Is it minus 18 across the globe? No. So she says it's easy peasy. What's gone wrong in this argument? Well, the argument's not wrong in concept, but what it hasn't taken account of is all the things that go on in the atmosphere that cause our climate. So here's a plot, and what it's showing is that sun radiation coming in on the left, the yellow bar, and there's the heat radiation going out on the right. That's the heat. So that's the same as in the previous picture. But now you see there's all these complicated arrows going on in the middle there, showing all sorts of energy transfers inside the atmosphere. Now, some of the radiation is reflected by clouds back to space. Some of it gets through to the surface. Then the surface gets warm, and it emits heat radiation, but much of that is absorbed in the atmosphere, and that comes down again, so there's more radiation coming back down than it was originally. So that's what we call the greenhouse effect, and that's called warming. But anything affecting any of these streams is going to affect surface temperature. So the first thing we're going to look at is scattering of light by clouds. Simon's going to make a cloud now.
Hopefully.
Yep. He's got the special gear on that you need to make clouds.
Well, this is going out on YouTube, so I thought I'd make sure I wear everything I'm meant to on my
Hope you can see the
assessment.
wires you're about to fall over. Yeah.
So I've got some dry ice in here, and this is minus about 80 degrees, hence why I'm wearing these. I'm going to pour it into some water, and Jo, you'll be able to see.
Mind the wires? Yeah.
Here we go.
Now what's happening is that this dry ice is making the air very, very cold.
Oh,
He's just about lost his camera.
oh no.
And the air gets cold, and the water vapour that's in the atmosphere all the time, we can't see it, it's here all the time, we just can't see it, but when it gets cold, it condenses out and you get tiny little droplets, and that's just like a cloud. If you've ever been in an aeroplane and you've been up through the clouds, you know it's white and bright. So it's white and bright, it's reflecting the radiation, and we're seeing it as white. But if we look in the infrared at the heat radiation, have we got that on now? Can we switch over to the heat camera, please? What we've got here is a camera that's measuring the temperature. And you can see this black bubbling stuff. Can we sort of move it around a bit?
Yeah.
No, don't burn yourself, no. You can see the sort of bubbling stuff, and it's all very dark, and the stuff around the outside is very bright. So what that's saying is cold is dark and warm is bright. In fact, you might have seen some of these infrared cameras on the telly when they're doing, what's that nature programme called, where they're looking at all the little animals in the dark and things. Springwatch, thank you. Yeah, so that sort of thing. So this is just to illustrate the idea that if something's bright in the visible, in light, it's not necessarily bright for heat. So we have to consider both streams. Right, I think we'll leave that bubbling away. We can have clouds being made, and we'll go back to the other. Oh, we'll have a look at. Oh, okay. Oh. So that's reflection by clouds, so that's what we've just been looking at. And I've just mentioned greenhouse gases as well. I'm going to come back to greenhouse gases in more detail in a minute. Oh, he's taking it away now. So if we're talking about gases in the atmosphere, here's some. Nitrogen is one of the world's most. It's about nearly 80%, 4/5 of the atmosphere is nitrogen, and about 20% is oxygen. And then down we've got about 0.04%, so less than 0.1% is carbon dioxide. That's all dry air. If we put some water vapour in, that varies over the globe and with seasons and things, it's about up to 4%. But what are all these gases doing? Well, I already mentioned about the greenhouse gases and the heat radiation. And if we now look and see which are the greenhouse gases, water vapour is actually the most important one. And it's water vapour in the atmosphere that's really keeping us in a nice, warm, equitable climate that's not the minus 18 degrees Celsius that I calculated on the first slide. It's more like 15 or 18 plus. So the water vapour's very, very important for keeping the planet nice and warm. But as humans, we can't really influence water vapour. We can put water vapour into the atmosphere. You can see he's trying. But it tends to rain out. If you get too much in the atmosphere, it just rains out. So we can't really control that directly. But what we can control is carbon dioxide. Now, you see that's only in quite a small concentration, but we'll see in a minute quite how important it is. Right, this slide, is Graph City. So I'm making no apologies. I love graphs. There's lots of graphs in this, and they're all showing the same thing. They're showing carbon dioxide concentration, or how much carbon dioxide there is as a function of time. And what we got in that first plot over there, you can see is hundreds of millions of years ago. This is an incredibly long time ago. And you see there's a tiny little 0.04% at the bottom there. That's what the concentration we've got today. And you see there's vast amounts of carbon dioxide in the atmosphere. But then the Earth was a completely different place, different landforms, different everything. Indeed, the first primate didn't appear on Earth. These are monkeys and gibbons and lemurs and all that sort of thing. Didn't evolve until a few million years ago. And you can see the carbon dioxide is getting lower there. And so now if we look less far back, now we're going hundreds of thousands of years ago. And you can see on that axis, the 0.04% is off the top. So now it's going below about 300. It's going up and down, which is quite interesting. I'll come back to that in a minute. It's going up and down, but it's always less than about 300, and that's hundreds of thousands of years. And humans first came on Earth about 200,000 years ago. So you can see that humans have been here. They haven't had those very, very high carbon dioxide levels. It's much lower values. If we get more recent, that's a boring plot, isn't it? But that's going over thousands of years ago, 2,000, 10,000 years ago. Carbon dioxide concentration is just pretty much flat at about 280. Get more recent still. This is over the past 1,000 years. And you can see it's flat, 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 flat. And then it goes whoopsie right at the end. And what's that whoopsie? Well, that whoopsie is this. And this is over the last 60 years or 70 years. Carbon dioxide. It's measured, see that says Mauna Loa, that's an observatory in Hawaii, so it's in very clean air. This is not industrial pollution. This is remote, clean air, and the carbon dioxide is going up and up and up and up. And you can see it over the last 5 years here. So what's happening here? You can see the carbon dioxide in the atmosphere. You can see these scales here. It's just got up to the 0.04% up there. Hasn't been as high as it is now since millions of years ago. And life on Earth hasn't been the same since, as it is now, since there's been carbon dioxide at these levels. And we also know that this is not natural. It's not somehow appearing out of volcanoes or coming some other way naturally, because we can carbon date it, and we know that it's very, very old, and it's coming from fossil fuels. It's coming from coal and oil and gas. And you can see the huge impact it's having. I think perhaps the most effective graph is the one in the middle at the bottom, where it's going on really flat, and then right at the end it goes sharply up. And this is the effect that humans are having on the climate. Well, does it matter? Carbon dioxide, 0.04%, it doesn't sound like very much really, does it? Let's look at that a bit further. So these are, this is the greenhouse gases, and I just wanted to first, before I carry on more about greenhouse gases, is to say a little bit about the sun. So, of course, you can change the greenhouse effect and change the greenhouse gases, But what happens if the sun's radiation was changing? Would that affect the climate? You'd think so. I said it's all the source of all the energy that's driving the climate system. So let's have a think about that. Now, what this is a sort of cartoon of the Earth going round the sun. And the first thing you notice is that the axis is tilted. So as the Earth goes around the sun, it's got tilting. And so when the southern hemisphere, South Pole, is tipping in towards the sun, that's southern hemisphere summer and our winter, northern hemisphere winter. And the other way, when the northern hemisphere is tipping into the sun, it's northern hemisphere summer. So that's how we get the seasons, with this tilted axis moving around the sun. But the other thing which actually isn't shown very well in this picture is that the orbit is not a circle, it's an ellipse. So it's a sort of squashed circle. And in fact, it's going nearer and further away from the sun as it goes round on this elliptical orbit. And that's important for understanding the effect on climate. So that says, if the Earth gets closer to the sun, it gets more radiation. That's rather obvious. And let's have a look at this plot. And this is showing the temperature of the Earth over hundreds of thousands of years, and it's going up and down. And you think, hang on a minute, that looks a bit like that CO2 plot I just showed you. And indeed it does. There's the CO2 again. And sometimes you hear people say, oh, well, it's all happened before. The temperature's gone up and down. The CO2's gone up and down. It's all natural. What are you making a fuss about? Well, here's the truth. In the bottom plot, the temperature's going up and down because of changes in the Earth's orbit around the sun. In fact, it's slight changes in this ellipticity of the orbit. And so that's making it go slightly warmer and slightly colder. Well, in fact, about 5 or 7 degrees warmer and colder. And you might say, well, these smooth orbits around the sun, you'd think there'd be smooth changes in temperature. And that would be the case, except for the fact that the greenhouse gases have a role. So if the sun makes it get a little bit warmer, then there's carbon dioxide and also methane, which is another important greenhouse gas, is released into the atmosphere. Greenhouse gas makes it warmer, more gas is released, makes it warmer, and you get this sort of positive effect, and you get that sharp rise in temperature. And it's only when the sun's effect starts to go off that it slowly declines again. So what's happening here is, the changes are initiated by the Earth's changing in the Earth's orbit, but then they're amplified by natural releases of carbon dioxide and methane. And that's creating these large changes in temperature. So far from being reassuring that, oh, it's all happened before, it's all natural, we've seen it, what are you going on about? Actually, this is saying that if anything forces the temperature to change, it could be the sun, or it could be indeed human activity, human greenhouse gases, then these positive feedback effects will also take place. So if we warm the climate, it will get warmer due to this effect on quite slow timescales, but what it means is it's not a reassuring story at all. It's actually a very worrying story. So that's the greenhouse effect. I've said I'd say a little bit more about computer models. I'm just looking at Simon. I haven't missed one of your demos,
Should we do the CO2 demo on the camera?
Yes, let's do the CO2 demo. Thank you. I thought I'd missed one.
So is it all right if we go over to the infrared camera, please? So you can see all yourselves out there. Wave. So we're about to see how CO2 actually... So you're giving off infrared radiation. The camera is detecting it. So you are giving off light, believe it or not. I'm going to hopefully come in.
So who's got the hottest face?
Can you see me there? There. So Annalisa, can you help me, please? So I've got some balloons of carbon dioxide here. This is just CO2 gas. So hopefully you'll be able to see as we... So I'm going to put... I've got them here.
Can you see Simon's face? It's the top...
I'm going to put one in front of my head. And I'm going to put another one in. And as we add more and more CO2, my head disappears. Because it's blocking out the infrared radiation. It can't reach the camera. And as I remove them, my head reappears, hopefully. Is it still there?
So we can see Simon's face with the visible light, but when the infrared light tries to get through the carbon dioxide, it can't get through. And the more carbon dioxide you have...
So you can see it blocking out people in the audience.
Oh, yeah.
So if you move down, you can see people waving, causing them to disappear.
Yeah, make that one disappear.
And there. So that's the impact that CO2 has upon infrared radiation. Thank you, that's safe. You can have that if you want. Thank you.
Thanks, sorry about missing your demo. So we can go back now to the other computer, thanks. I was going to tell you a little bit about computer models. So when you look at the weather forecasts on the telly, and you see all these charts and maps, they're all produced by computers, and the Met Office runs these incredibly complicated, well, they're not actually very complicated, I'll tell you the basics in a minute, but quite large models of the weather to forecast what the weather's doing. So what is the science that's going on behind those computer forecasts? Now, I'm going to put some physics in here. I'm sure you all love physics. Good, hooray. So we're going to put a bit of physics in to explain what's the basis of the weather forecasts. So the first one is Newton's second law. Anybody doing GCSE physics? Yay! So you all know Newton's second law. Force is mass times acceleration. So in this case, we've got a massive atmosphere, and we've got various forces acting on it, which one of us gravity. You've got forces associated with the pressure gradients, pushing it to and fro. You've got forces associated with the Earth rotating. And you've also got other forces like viscous drag and all these sorts of things. So if we can write down all the forces, then we know how the air is accelerating. So we know the wind. Next one, conservation of mass. So if the air goes from somewhere to somewhere else, it can't disappear. It's got to either go somewhere else and or get squashed. Conservation of energy. So if there's heat coming in from the sun, it's going to make the air hot, and the air can lose the heat to space with the infrared radiation, or it can expand, but the energy is conserved. And the final one, is this year 9, gas law? Do you do gas law? So, yes, somebody said yes. So we've got PV is RT, and I see Simon's got his helmet on again. So he's
I don't like wearing this, but... So here we have some liquid nitrogen. So this is minus 200 degrees. And we're about to see how the pressure times the volume equals temperature. So basically, if you think about it, temperature and volume are linked. So if you make something colder, it gets smaller. So I've placed inside here a balloon earlier. And that is at minus 200 degrees. And now it's warming up. And I've got another one.
Put the other one, can you put the other one over this side? Oh, okay.
So it was quite small. And now it's starting to get bigger and bigger and bigger. And that's simply as the temperature increases, so does its volume. So that fitted into a tiny little space.
Where's the other one gone?
Down on the floor.
Right, you'll never forget PV is RT now. Yeah.
Oh, no. Definitely won't. So to finish off the story about the computer modelling, so here we are, we've got very, very basic laws of physics, ones that you can understand, and what we do is we write them all down, and we've actually got 6 equations for 6 unknowns. So it's 6 because actually, when you look at the first one, the acceleration for the wind can be going north-south or east-west or up and down, so actually that's 3 equations. So we've got essentially got 6 equations, and we've got 6 unknowns. That's pressure, density, temperature, and the wind in 3 directions. Now, you may have done simultaneous equations, perhaps, in maths, and you've done 2 equations for x and y, and you can solve for x and you can solve for y. That's 2 equations for 2 unknowns.
if you've got 6 equations for 6 unknowns, you can also solve it. It takes a bit longer, but you can do it. And so this is it. This is weather forecasting, essentially. There's a few other bits and pieces need to go in there, like heating from the sun and all the rest of it. But this is it, in a fundamentally, what weather forecasts are doing. And so what we have to do is we write down those equations, and then we solve them for the conditions appropriate on little bits of grid. So here's a 3-dimensional grid over the globe. And we solve those equations every sort of 6 hours and integrate in time and see what happens to the weather. So actually, you see, it's the same as Minecraft, except that Minecraft has rather more detail, at least this version does, has rather more detail than the climate models. Here's a typical climate model grid, so you can see Minecraft is doing better, although I don't think Minecraft can forecast the weather quite yet. So the physics is good, but we have to remember that the real world is quite complicated, and we can't actually resolve, we can't see, we can't picture these tiny little, beautiful little clouds and lovely scenery that we've got in the real world. So we are making approximations, even though we've got this rather wonderful physics. So you might say, if you're having trouble forecasting the weather over more than about 10 days, the weather forecasts sort of give up after about 9 or 10 days, how can you possibly predict the climate? You can't do it 10 days. How can you possibly do it for 100 years? Well, the answer to that question is that you're not predicting the same thing. When you're predicting the weather, you're saying, what's it going to be like in London next Thursday? When we do climate predictions, we're not doing what's it going to be like in London on Thursday in 2050 or something. We're doing what's it going to be like in the general area of Western Europe sometime around the winter in 2050. So we're doing typical, we're not doing precise predictions, we're doing typical or average values over regions. So the averaging over space and the averaging over time is much broader. But we can run the same forecast models to do that too. So when we look at this graph, which is what I showed you right at the beginning, the question is, can we explain the shape of this global warming? And if we use the climate models, we can get a pretty good idea. So the plot up there, the black, is the same temperature curve I keep showing you, just on a different plot. And the colours are lots of different climate models trying to reproduce that black curve. And in those models, they've taken account of the greenhouse gases, of industrial pollution. So if you've got particles in the air, they scatter the sunshine back to space. Of land use, so if you get areas that are deforested, they get brighter and they reflect sunshine back to space. Of changes in the sun, the small changes in the sun that actually influence the climate. Volcanoes are quite important. They chuck a whole load of stuff up, actually right up into the stratosphere, and that's floating around in the atmosphere and again reflecting sunshine to space. And there's measurements that show the cooling over the globe that follows a big volcanic eruption. And also, importantly, energy into and out of the oceans on a sort of rather slower timescale is very important in determining some of these shapes. So what you can see is that each particular climate simulation, each one of those little spaghettis, is not doing the black thing, but altogether, they're getting a pretty good picture. They're getting the broad spread of the climate warming as we go recently, and they can also get much of the broad shape. So you can see there's a dip in about 1981, that's a volcano, and then we've got the climate warming due to the greenhouse gases subsequently. So we can't do it precisely, but we can get a pretty broad idea, a spread of ideas, which means that we think that we can have a little bit more confidence in our ability to predict what might happen in the future. Another important point to make is that when we talk about global warming, and so far I've just shown you pictures of global average temperature, it's not the same everywhere, not at all the same everywhere. So these are measurements of the temperature difference over the globe over the last 100 years or so. And you see there's been large changes over the continent of Asia and also over some parts of South America. I should say that the white areas is where we don't have enough data to be able to say. But there's some places on Earth which are warming much less, and indeed there's some places, including just the North Atlantic there, which appear to be cooling slightly. which is quite intriguing. We're not quite sure why that's what's causing that, but it's probably something to do with changes in the ocean's circulation. So it's not warming the same everywhere, and some places may even be getting a little bit colder. So when we talk about global warming, it's not warming everywhere. And the other side of that story is that if you've got a temperature record from one particular place, you can't use that and say that's the same as is happening everywhere over the globe. You have to have a bit more information. So this is using the climate models to predict the change in global average surface temperature. So, of course, in order to predict the temperature, we need to predict the CO2. That's much more difficult because you need to know what humans are going to do and what the economies are going to do and what sort of energy we're going to use. So here there's two examples. In the red example here, we're continuing to emit CO2 more and more and more, just like we're doing at the moment, carrying on going. And in the blue one, the CO2 emissions peak in 2020 and they actually go to zero by 2075. So that's sort of near the end of this plot here. So, of course, with the red one, it's just carrying on going, warming and warming and warming, and it's up to about 4 or 5 degrees by the time you get to the end of the century. The blue one, although the CO2 emissions have got to zero by 2075, you can see that the temperature hasn't gone back to where it started by 2075. And this is because CO2 is very, very long-lived. It's got a lifetime of about 200 years. And so once you've got it in the atmosphere, it's going to stay there having an effect. Even more than that, the heat gets into the oceans and then it takes a long time for it to get out again. So there's a very, very sort of drag effect. If you stop emissions today, the temperatures wouldn't stop rising today. So I've talked a lot about temperature. What other evidence is there for climate change? Here's one. This is looking at Arctic sea ice. So there's a seasonal cycle in Arctic sea ice. There's less in the summer and more in the winter. And this is its minimum area in summer, and you can see the difference between 1979 and 2011, and how much it's decreased over that time. So that's just an indicator of the warming that's taking place as less ice in the summer. Another important point to be made is that if you have less ice, it means that the surface is darker. So even if it's land or sea, where it's not ice, it's dark. So that means you get less reflection of solar energy, which means you get more of the sun's warming, and that enhances the warming that's caused the original melting of the ice. So I think we're going to do a demo, are we, Simon? Yep, right, good. So this is very high tech, yeah. He's the dark surface, and I'm the bright surface.
Got your thermometer over there, Joe?
I've got it somewhere. Yeah, here we are. So we got some infrared thermometers here.
So mine is...
sorry.
Yeah, sorry. What's your initial temperature, Joe?
22.7.
Okay, mine is 21.9.
Okay, so mine's a bit warmer.
Okay, let's try and warm it up.
So now we're going to put them into the sun here.
So, oh wow.
Mine's still 22.7.
Mine has gone up to 24.3.
Already?
Yes.
Blimey, that's quick.
It's climbing up quite rapidly.
22.6.
25, going up to... So
22.
this is shooting up 25.1, 25.2.
I'm still 22.6. So this is a simple example of how, and you'll know this from your own experience anyway, if you have dark things, if you're wearing dark things, you get warmer than if you're wearing white things to reflect the sunshine. But this is happening on the globe as well, so when the ice goes away, it means you get more warming to enhance the original warming. Okay, good. Yeah. So this is sea ice, and this is ice that's floating on the sea, as it says. But of course, you also get ice on land, and what we've got here at the top on the right there is a picture of the Greenland ice cap. And on the bottom right there, you've got a melt on the Greenland ice cap of the water draining towards the sea as it's melting in the summer. And on the graph on the left there, it's sort of going up and down and up and down. And each of those bars is a different century, so a different 100 years. So it's starting off 2,000 years ago, And you can see sea level rise. It goes up and down, up and down, up and down. But look at the one on the right there. That's the 20th century. So sea level is going up. And it's going up partly because of the oceans are getting warmer and just expanding, and partly because of melting of ice on land. And I think we're now going to have a picture. Hang on, I've got a picture. So we're going to show you why melting ice on land is important and melting ice on water isn't important. And first of all, so we've got this very high-tech scientific equipment in the middle here. Do you want to explain it, or shall I?
You can. Do you want to show the pictures from earlier? Sorry,
yes, I do.
If we go back to the original... So we set this running.
Yeah. So I was just going to explain what it was first.
Sorry, yeah, please.
So the idea here is that this is ice on land, so it's Greenland or Antarctic or something. And this is ice floating in the water. And we set this up about before 3 o'clock. And this is the photograph taken from this side, so it got a bit drippy, of the 2 tanks. And you can see that the water level is equal. And then we've got, over time, we've had the ice melting. And now Simon's going to show you, there's a little camera sitting here to monitor what it's doing. So I think you can see that the green water is now significantly higher than the water on the left. So ice floating, if ice floating melts, it doesn't make any difference because it's already occupying some space in the water, so it doesn't make any difference to the level when it melts. But if you've got ice on land, it melts and then all the water drains into the sea, then that has an effect. So one of the things that's very difficult to predict in the climate is if and when and how the ice sheets might melt. If they did melt, and this is not going to happen immediately, but if they did melt, then each of those could contribute tens of meters to sea level rise. This is absolutely horrific. We can't even think about this. So, you know, that's looking very far ahead into the future, but it's a serious worry. So if we could go back onto the other computer, please.
I think it's on YouTube.
What? What?
I think that is your computer, Jo.
Trick me. Sorry. It was my computer with the photograph. Right. So this is computer models predicting global sea level rise, and again we have to have the bad scenario and the not so bad scenario. And what you can see here is that the not so bad scenario, even though that the CO2 emissions decline to 0 by 2075, etc., the sea level is carrying on going because of this very long inertia in the system. So we're up to about 3/4 of a metre in the bad one. If we went to 2150 at the current rate, this is some simulations of what might happen on the North Sea. So we can see that half of Holland is underwater, and bits of Cambridgeshire, and then we got the Thames Valley, and significant bits of the edges of the Thames are underwater, and I'm afraid the Thames Barrier is going to do nothing under these circumstances. So we do have to, this is a long time into the future, but we do have to be prepared and think about what it might mean. Other impacts of climate change, well, of course, these sorts of things are very difficult to predict, but we do need to think about them. If we have, the sort of irony is that some people will be suffering from too much water, they'll be getting flooding and storms, and other people will be suffering from droughts and water scarcity. And these estimates, of course, are very difficult to do, but you can see there's very large numbers involved. Heat waves, huge, loss of cropland because of loss of the, not only of the water that's needed for the crops, but also the soil gets degraded. So these are all sorts of things we want to try and avoid. And so this is the message. Sorry I'm banging on about this, but I really do think we've got to do something about putting greenhouse gases into the atmosphere. So a wonderful thing was the Paris Agreement. It's 2 years ago now, so some of you may remember it. And all the countries, something like 195 countries in the United Nations, unanimously agreed that they do something about it. And this was quite remarkable. It's never happened before in the United Nations. And they ratified the treaty faster than any other treaty's ever been ratified. This is all incredibly positive. And they're aiming to keep global temperature rise to less than 2 degrees above what it was in about 1850. And actually try and do it less than that, to 1.5 degrees. So this is a hugely positive international agreement. But of course, then it comes down to how are we going to do it? And some countries are doing more than others. Say no more. Right. So a lot of the way that we burn energy is for coal and oil and things to produce carbon dioxide, and we need to think about how much energy we need. So in the UK, each person needs about 4,000 watts. That's something like, I don't know, 100 light bulbs on all the time or something, just to satisfy all your needs. If you go, how much do we need in England? Well, it's 200 billion watts, or we call that 200 gigawatts, because the units are getting a bit big. If we go to the total human power consumption at the moment is 16,000 gigawatts, and now we're into terawatts. You can see the units are getting bigger and bigger and bigger. That's a big number. 86% of that at the moment is from oil, coal and gas. So these are the fossil fuels that we need to do something about, because they're the ones that are making that CO2 curve go right up. Now, let's think about the sun. I talked right at the beginning about the sun and its energy. The sun's putting out a huge amount of energy, and the sun, the power absorbed by the Earth, this is not the energy coming out of the sun, total, this is the energy absorbed by the Earth, total. 120,000 terawatts, that makes that 16 terawatts look a bit small. And of course, this solar energy is doing all sorts of things like driving the weather and all sorts of other things, but it does enable you to see there's an awful lot of energy available in solar radiation should we choose to use it for energy provision rather than fossil fuels. So this is getting onto the sort of politics side of things now. The UK had a Climate Change Act back in 2008, and it set in law, and this is unique in the world, carbon budgets in 5-year chunks going ahead. And this is showing annual emissions of carbon dioxide. The black is what's happened, and the dotted line is where we need to get to. Now, so far, so good. Obviously, the first bit is the easiest. And the dashed line is moving slightly away from the dotted line, which means we're not quite meeting the targets. But this is what the UK has said it's going to do, and the fifth carbon budget is in law. So the government's got to do something about it, which is very good. And here we are on thinking about renewable energy. So I mentioned solar energy there. Of course, if you're around the UK, wind energy is absolutely phenomenal, especially offshore wind can be providing quite a lot of our energy needs. And this rather blurry graph at the bottom is just showing different sorts of renewable energies in different colours. The purple is the sun, and I've forgotten which one is the wind, onshore wind. Offshore wind is the blue near the bottom. So they're all expanding. Not enough yet, but it's interesting that in 2015, 25% of electricity generation was from solar and wind. Now, energy is not just electricity, so that's not the whole story. But this is, again, is a positive story, and I hope we'll continue to develop it. So finally, just to say, what can we all do? It's not a sort of all or nothing. It doesn't have to be if you can't do it all, then you shouldn't do anything. Everybody can do their little bit, and you can think about the little bits that you can do. First of all, save energy. We can all do that. Just switch off the light and turn off the heater when you're not in the room. If you have a choice, try and choose renewable energy sources. Create less waste, all kinds of waste. Food, water, materials, as well as energy. Everything is using resources that we could save and use less energy and other things in the future. Try to walk or bike. We can't do it all the time, but perhaps we can do that more than go in the car occasionally. Think about it. And another important one is just a bit less meat in the diet, because farming meat is far more energy intensive than growing vegetables. So I don't want to lecture everybody about this, but just think about it as you go ahead in your lives. And I think I'll leave it there. Thank you.
Oh, thank you very much for that. That was really brilliant. Thank you for that very informative and very important lesson. And I've taken away 2 things from this. Global warming is really bad, and physics is really fun. Okay, we're not going to forget that gas law, are we? I think that was really good. Thank you very much to Simon and Jo. That was absolutely brilliant. Thank you. Yes, another round of applause. Thank you.